Welcome to Astronomy, Chapter 13. This chapter is going to be about the deaths of stars. Now, the death of stars chapter is a fascinating area to go through, where we're going to be looking at the end stages of what happens to these bright lights as they go through the final parts of their evolution. And if you remember, the important part from earlier about how these stars progress is directly related to mass. Don't forget that part. We will be coming back to that effect as we go through this. And in fact, the first section that we see here starts off with the idea that low mass stars, they end up as planetary nebula. So if a star has a little mass, it has a fizzling out effect is basically what that means. Now, this is one of many, many examples in astronomy where things have a name associated with them. And the name is given early in the discovery of an object. And it turns out that the name, for what we thought it was, is totally wrong. But the name ends up sticking. And planetary nebula is a great example of this, because these nebula that we see have nothing to do with planets. There's no planet involved here. So it's frustrating in that regard. But nonetheless, planetary nebula really basically just means, the idea is that if a star is low mass, what will happen is eventually the center of the star will cool to the point where and there's not enough gravity to hold this thing off, and the star will simply fall apart. Now, as you're going through your reading on 13.1, it'll explain the details of what's going on to form these planetary nebulae. But nonetheless, that's the basic idea. They're simply falling apart. A great example of this is shown here on page 419 when you're up at the top with the Ring Nebula here, which is a beautiful object that we can see in... this is the Helix Nebula. Looks an awful lot like another one. This reminds me of the Ring Nebula. The Ring Nebula is an object that I hope to show all of you in this class that is a planetary nebula. That is visible very nicely from the northern hemisphere. But nonetheless, the planetary nebula is a sloughed off layer of material that falls apart, and what's left in the middle is a small white dwarf. Remember, white dwarfs are a relatively hot star, but they are very small. We see them here on the HR diagram, that they are the center of what's left over from the initial falling apart of a low mass star. Now, white dwarfs can also do something else. And in 13.3, they talk about the idea of this thing called a nova. And a nova just means to shoot out light, is really what the name means. And to go through this process of nova, what happens is, effectively, a star goes from being very, very dim to being very, very bright. Those are the same objects this is after a nova, and this is while it is going through the process of nova. This is where the star is emitting a large amount of its hydrogen material, and it explains how this process works when you read through 13.3. That's an important concept to understand a nova. Now, this is not to be confused with a supernova, because a supernova is a different process. And in fact, supernovae are broken into two different types. That is, type 1a and type 2a are the ones that we're really going to look at in here. And white dwarfs can also go through this process of supernova. And then you need to read through that to make sure you have an understanding of how those particular nova work. But what I want to point out, why these things are relevant. It's one thing to be able to see a star, explode into this brilliant beam of light, but what does that really do for us other than being a pretty fireworks show? Well, here's what it can do for us. We see that this is a light curve. This is the luminosity, which is the measurement of brightness. And certain types of stars will go through these two different types of supernovae. And what this does is the brightness, the maximum brightness, is a known fact, is a known variable. And so if we know how bright this is, if we know the absolute magnitude, and we measure the apparent magnitude, what we can do then is we can use that formula that I showed you back in chapter 11 to determine distance, and explains this process as you're going down through on page 422. This ends up being a very useful application for supernovae. They're not just something cool to watch them explode, but this does end up being very useful. I am particularly amused over here by this comic where that is talking about the confusion in the naming here, where these two astronomers are looking at a bright light spot on here. It says it's somewhere between a nova and a supernova, and probably a pretty good nova. But nonetheless, there is a bit of confusion, although ultimately it's a matter of what is going on with the mass of it. Now, if a star is or equal to or greater than about 8 solar magnitudes. Now, we're talking about stars much bigger than the sun. Remember, the sun is a very common middle-of-the-road maiden sequence star. But if we find these really massive stars, the fusion process inside of them causes it to not stop with the helium. It does not simply go hydrogen into helium and then it quits. If there is enough gravity, what happens is it forms multiple layers of where the fusion process continues. So we see hydrogen forming into helium, and then forming into carbon, and then to neon and oxygen and iron, and forming these heavier and heavier elements. Now, these elements are quite rare in the grand scheme of things. In terms of us being able to find, silicon and oxygen and iron, these objects are these by percentage in the universe. We do not find these elements very often. The Earth happens to have a substantial amount of them, conveniently, because all of these can be made, or at least we think are made, inside of a large supergiant star. Now, what they're trying to show you here is that this supergiant star is so big, it's roughly the size of the orbit of Jupiter. Now remember, Jupiter's orbit is about 5 astronomical units. So we're talking about many, many, many times bigger than the sun. Some of these are, in terms of their size, end up being up to 1,000 times bigger than our own sun. Just massively big stars. These massively big stars are responsible for forming, or can form, a substantial part of the elements we find on the periodic table. So this is very useful in terms of putting these extra elements in the universe through significantly higher fusion processes. And of course, when eventually there is a point where this process stops, and when this stops, it stops right here with iron. Now, for reasons that are beyond the scope of this class, iron is the spot where fusion stops. Iron does not fuse into more. I'll say it like this. It's as simple. Iron is an efficient, it's iron 56, is one particular isotope of iron, is very efficient in terms of its storage of protons and neutrons in its nucleus, and therefore it does not go through fusion. We do not see this happen. We do not see iron being fused anywhere else. So that means that iron is the stopping point inside of a star. Now, when this star dies, when it goes through the end, we see a massive, massive explosion. Because eventually what's going to happen is if that star cools on the inside, if there's no fusion going on, eventually the star is going to grow more and more iron in the interior that is cooling off, and the star is going to grow larger because there's a core inside a material that's not growing, that's not doing any fusion. And so the star will get massively large, and as it gets massively large, eventually what will happen, and it's explaining all this on 424, what happens with the star eventually is it will crush down on itself. If it is a massive star, if it's more than 8 solar masses, eventually gravity will win, and the star, all that material, will not be able to be held by the pressure inside anymore, and the star will collapse down on itself. When it does this, all of that material will close in on all that empty space, and eventually it will all hit that core in the center. And in doing so, this one process appears to be responsible for forming all of the other heavy elements that we find on the periodic table. So everything past iron appears to be made out of a supernova. So that process is vitally important in understanding this is how we're going to see new stars being formed. This is how new elements and new materials are being formed. The supernova ends up being a crucial event to put new material out in space. And if you look on 426, they give you some examples of where we see this. We see the remnants of these supernova in many places. One of my favorites they don't have in here is the Crab Nebula. But the Crab Nebula is a beautiful object that is a supernova remnant that was observed several hundred years ago exploding. And has since faded, but is still very visible. They also talk about in here, taking a look at if you look on page 427, this is the supernova that was observed by Tycho Brahe. You remember Tycho Brahe from way back in chapter 2 as one of the people who was an early astronomer who watched and studied the stars very closely. He actually observed this event back in 1572, this original explosion. Now, there's something exciting going on inside of this, because if you look at what they're talking about, you see this tiny, tiny, tiny little dot of light in here. Talking about this something we call a probable neutron star. Now, what in the world is a neutron star? Well, you take a look over here and when we get to 430, you read about what neutron stars are. They are effectively stars that after all of this collapses down onto it, where we have basically stripped the star of all of its electrons, and we effectively have a star of nuclei. Now, I don't know how much you remember about chemistry, but what you ought to remember is that we have protons and neutrons in the nucleus, and then we have the electrons going around on the outside. And if you think about this for just a second, I'll give you a quick drawing here, where you have our protons and our neutrons in the nucleus, and you have these electrons out here, and they don't go around in circular orbits. It's certainly not two-dimensional either. But what I want to point out is that in here, there is loads of empty space. And in fact, it turns out the nucleus is very, 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 very small. The best analogy, or one of the best analogies that I've heard on this, is if you were to think of the nucleus of an atom as a baseball, the electron cloud around it, the area of electrons around it, would be on the order of the size of a baseball stadium. So imagine taking nothing but little baseballs and packing them together instead of having all that empty space. And what you have with a neutron star then is you have a area, or you have an object that has a almost unbelievably high density, an incredibly strong density, because all of that empty space effectively, or at least almost all of that empty space, has been removed. And in doing so, we end up with these tiny, tiny little objects with massive densities that have massive gravities. Now, moving on from that, they talk a little bit about a pulsar. Pulsar meaning a pulsating star, talking about a pulsating neutron star that allows us to be able to form another method for being able to measure great distances. So here we see an example of one that is on, and it is pulsating its light. Here it is not on. And if you go through the reading on 430, it explains why we have some areas that are going to be creating this significant light change. Now, they also give you a little bit of a model of what we think the inside of a neutron star would look like. This is in section 13 on page 434, talking about the densities of what we're looking at here. Now, you have to look at this. This is staggering numbers, but I wanted to point this out. We're talking about the distance here is like 10 kilometers. Okay, 10 kilometers is the size of what? Like a city? Like a large city? Something like that. 10K is a lot of people run a race that's 10K. That's a short race for some people. Okay? And we're talking about a density that is on the order of billions of kilograms per cubic meter. For reference, water has a density of about 1,000 kilograms per cubic meter. Our heavy metals are maybe 6, 7, 8, 9,000. And now we're talking about billions of kilograms per cubic meter. An unbelievably high amount of density coming from a neutron star. Neutron stars being a very, very tightly packed object. Okay, the last thing I want to share with you. You definitely got to see this on 438. This is one of those things, one of those diagrams you got to look at, got to know. On 438, it's talking about what's going to happen to a star. I'm giving you an idea. And remember, everything that's going to happen to a star depends on its mass. So, you look at this, it's telling you the increasing mass. If it's a low mass star, effectively it's only going to become a red dwarf. If it's a medium star, it's going to go through a main sequence and a giant star. And then if it's up to 25, it's going to go through supernova and become a neutron star. The last one, oh, that's an interesting one. Because if the most massive, biggest and the baddest of them all, if it's greater than 25 solar masses, eventually it will become a star we call a supergiant. And when it goes through a supernova, oh, now we have a whole new characterization of things that it comes into as a black hole. And we'll talk about more about black holes as we go throughout the end of this course and the theoretical physics behind them. It's very exciting stuff. But this one chart really sums it up pretty nicely. And so if you were to think about all of the stars in the universe, the vast majority of them are actually like our own sun, a moderate amount of solar mass, and that would put it right here in the middle of this chart. And so in doing so, we would see that the projected evolutionary path for our sun would be to become a giant and then a red supergiant, and then eventually fizzle out as a planetary nebula. Here we see the Helix Nebula, and then the star itself becomes a white dwarf. Now, obviously, by the time the sun goes through any of this, goes to being a red giant, or especially a red supergiant, we would surely die. But if the sun were to grow much bigger than it is currently, the Earth will cease to exist pretty quickly. The good news is, this process, we think that sun's probably got about 4 or 5 billion years before it's going to go through that. So we've got some time. We're okay there. But that is the specifics of the things you need to know what's going on in Chapter 13. Again, make sure you're keeping up with your reading. Take a look at the PowerPoint associated with this chapter, and you should be getting ready to do the homework then for Chapter 13. Good luck.